Okay, can you, I supposed to be back online? It's back online. Yeah, so what happened was that my computer was overheating and I decided to simply to go down. There's nothing that I can do in that particular occasion. So I was just about to explain that, what is right off the delta generalized coordinates is called generalized externally applied forces. And that is the trick that we are looking here. So it is actually mapping the force expression from global coordinates to generalized coordinates. And that's what we practiced last week. And now today what we're going to do is that we will extend the same concept to generalized inertial forces, or inertial forces in general, which first will be expressed in global coordinates, and then a little later we will express them in using generalized coordinates. Now, one of you guys sent me an email that there was a typing mistake 2 weeks back, and the typing mistake was this was last week actually. It was related to this mapping matrix. And now, if you look at the mapping matrix, how it was written in original form was full of mistake. So this component should be, of course, sine. This supposed to be then cosine. And then this supposed to be ux, and this supposed to be cosine, and this supposed to be sine. So it was, very incorrectly written. So the correct version is this one that is shown below here. So again, I would like to apologize that typing mistake, and I am going to fix that to next year lectures. All right. So now what follows is this painful topic. So subject matter, what we're going to discuss, as I mentioned, is that, the most difficult one that you have ever seen in your life before this. Believe me, trust me, it's going to be painful mathematically, and we are not even leaving there. So we're going to even continue, continue about how is augmented formulation, and that concept will make your mind to blow. But we'll see. I will see how it's going to be today. So let's get started from generalized generalized inertial forces, and now you know the concept how it works. So it works in such a way that we first look how is the inertial forces. Remember, the inertial forces is a mass multiplied by acceleration. That's what it is, inertia. Okay. Now, because we are dealing with the particles, so we cannot really express it in a way that the mass multiplied by acceleration, but instead we have to look at the density of each one of the particles that is within the boundary of the body. Okay, so say that we have here a potato-shaped body, and now it's full of particles. So it consists of infinite number of particles, and we have to account all of them in order to describe the inertia of this body. Now, how we can make that happen? Well, we can make it happen by adding up all the particles and the density associated to particles. Mathematically, it can be expressed by using the volume integral in such a way that the volumes or the boundaries of this volume integrals are boundaries of the body. And then what's inside of this volume integral is a density at any particular position of this body. So that's how we can do it. But what this is actually, that's an expression of inertia. But it's just a little bit more sophisticated way to do it. So this is the way that we say the inertia. So this is a mass. So we're counting the volume multiplied by density. You know that that's equal to the mass of the body. So don't get confused about the notation, please. It's just a notation, but it means mass for us. So eventually what this is saying mass multiplied by acceleration. And acceleration is r dot dot. That's what it is. Okay? Clear? Okay, that's a force. And we concluded that, there is according to Newton's second law, that mentioned that mass multiplied by external applied force is equal than the mass multiplied by acceleration. Then came Delon Pratt into play, and he said, okay, this equation can be written like this, and became world famous. We even know his name because of this. It was a little more than just this. He figured out that inertia forces, this one here, can be treated same way than external applied forces. Okay, so if that's the case, let's use the same concept. Let's use the concept of virtual work, and let's look how much inertial forces are making the virtual work. How we can make that? That will be obviously force multiplied by, yes, virtual displacement. Virtual displacement. Okay, why we do that? Why we do this whole thing? Again, we have to do it because the force expressed here is expressed using global coordinates. How can I know that? How do I know that this is expressed in global coordinates? Well, I know that because, you know, r, this one here, that one here is an expression of particle acceleration with respect to global coordinate system. So this one here consists of two components that are r dot x, r dot y. So that's what tells me that this force is expressed in global coordinates. And I want to express the forces using generalized coordinates. Okay, so let's make it happen. So let's take the virtual displacement and let's multiply the virtual displacement by inertial forces. All right, that's how it's going to be. And you know, when I take this definition, when I do the substitute the definition of inertial forces here, that's how the virtual work associated to inertial forces look like. Okay, good, but not really what we are after, because we are really after this mapping. Remember the mapping? We will take the mapping in our toolbox again. The mapping tells that the delta R is equal then partial R partial Q multiplied by delta Q. It sounds like, okay, this is just a bunch of math that makes absolutely no difference. But look exactly, you know, what are the two things that this equation are relating? It is relating delta R and delta Q. Delta R is a global coordinates, delta Q is generalized coordinates. So that's where the mapping is. And this matrix here is exactly the mapping we're looking after. All right? So let's use it. Let's substitute that to previous equation. That's how it reads. And now again, everything that is, you know, separated from delta Q, that will be called as a generalized inertia forces. Generalized inertia forces can be written as it is shown here. So this is a force expression using generalized coordinates. Still not really easy to use because we have to do a little bit of substitution to make it a little bit useful. This is kind of like a raw material. And what we're going to do for this raw material is that we're going to use a serious mathematical manipulation. Let me emphasize, serious mathematical manipulation, and it's serious. So now I'm sure you need to, you know, you will be very surprised what you're going to see within the, you know, within the next slides. But it's going to be, you know, mathematically quite challenging. But think about all the time, what is a main objective we want to do here? So we want to express inertial forces using generalized coordinates. That's what we wanted to do. Okay, let's see if we are really able to do that. Okay, now prior to substitution, before we actually substitute in the velocity, excuse me, the acceleration to this part of the equation, so let's rewrite the expression of acceleration. Second lecture, I think that this was a second lecture, we concluded that acceleration can be put in a writing by using three components that are translational acceleration, and then the tangential acceleration, normal acceleration due to the angular velocity, and tangential acceleration due to the angular acceleration. So three components. And now I'm going to express this very same equation by simply reorganizing the equation such that velocity of generalized coordinates are expressed as a one separate vector. So look what I do. I take this one here, I put it as a separate vector. I change the order of these two components, and I take this theta dot dot. I will put that together with this r dot dot. So that's how it reads. So this is just the reorganizing things, nothing else. What's left is this guy, the one that depends quadratically on angular velocity, right? So that's what is left. You guys still able to follow me? Yes, sir.
In the upper line there's a square, and where is it in the lower line? There's,
oh yeah. I see that too. So you're wondering where that is disappearing.
yeah.
Okay. Yeah, I see the same here. I was hoping that no one actually is able to recognize this. It was just a hope. You know, where this power 2 is coming from. Okay, this is obviously worth of coffee or even maybe lunch. At least coffee. I owe you still coffee, I remember that. So where that power 2 is coming from? Make a guess. There's a clear explanation for that. Not related to mathematics, not related to multi-body dynamics, but any guesses? Let me say it's something that is between this seat and this keyboard. Okay, any idea? It's a typing mistake, so I owe you a coffee. So it's a clear typing mistake. So I see that this is, where this one here has never been here before. And now it suddenly came, like out of the blue sky. How? Because of the typing mistake. It's my typing mistake. You'd go and reference or check out your notes from the previous lectures, and it's not there. And now it suddenly appears. And I know why it is appearing here. Because of this annoying copy paste. Obviously I'm taking this component and I copy it here, and I forgot to delete that power 2. So my mistake. Sorry to confuse you. All right, so what's left? This guy is left. And then I have here acceleration of generalized coordinates, and then this component that is related to angular velocity. All right, now we're ready to do the substitution. So we're ready to go ahead and do the mathematical mess. So I'm going to take, acceleration, put it here. I will take this mapping, put it here, and it's just going to be, bunch of matrix operation. That's what's going to happen next. And the mathematical operation look like this, because, and look, there is this transpose operation that complicates everything a little bit. But simply I substituted the acceleration, I substituted the mapping, and then the mapping appears to be here. This is the guy that came from acceleration, and this is the component that came from the acceleration. Now I simply have to multiply this and this with the mapping. Okay, so let's do it. Let's compute it. And okay, this was what I got from the previous slide. So this is still not multiplying, so I have to multiply this with this guy and with this guy. When I do the first multiplication, something that appears to be symmetric comes into play. And something that appears to be symmetric will be later called as a mass matrix. The mass matrix is what it is called, representation of mass and inertia properties. How that will be in the details, we will take a look at that in a second. But you can get this by multiplying this vector by this vector. What you're going to get as a result will be 3 by 3 mass matrix. And then I have here another component that will be later called as a quadratic velocity vector. Okay, now I have a question to you. If there's going to be in-class quiz right after this slide, do you have any chance? Absolutely no chance to answer correctly. Because, okay, let me ask, is this making any sense to you? Or none of this stuff make any sense? Okay, I understand that none of this stuff make any sense. Because you came here with B's. And I started to fight against you. I saw, okay, this is, how the world is. And this is the mathematics related to this course. And I understand that you're in a shock. I understand that. I have some good news. Would you like to hear it? I will not ask any of this stuff in written exam. I will not ask. I'm not saying, okay, so the first question, so derive me mass matrix starting from the Big Bang. It's not going to happen. But I might ask physical interpretation of all this. What is a physical interpretation? You have absolutely no idea, because this was just a mathematical background. Now what follows is that we will actually start looking, okay, now this is what we got. It's what it means for us. So what is the value of all this? And where we actually need this? Is this just, the nice to know that, we can do these mathematical tricks, or is this really some value? Here's a value. Let me step to that value part, because that's what I could ask in written exam. I will never ask this kind of, derive me this and that. That's unrealistic, because the best possible scenario, you could memorize the deriving few minutes, and then it will disappear from your head. But this physical interpretation, I hope you will keep it in your head as long as possible. Okay. Make you feel better or worse? A little better.
Camera and the big pros.
Yes, of course. Okay, so let's see if this is going to help. So is this one? Yeah, what I need to do is that I need to put the integrated camera first, and then to put another camera back, and it's back on. What a painful business with the YouTube. I don't think that I will ever be a professional YouTube person. Two reasons. First of all, this is quite painful. Another bigger problem than that is that I got 75 subscribers. So I don't think that I can make a living out of that. So I need more subscribers. 75. How much money I can get from the YouTube with the 75 subscribers? 0. What? No money.
It's not based on subscribers, it's based on views.
Oh, in views. Okay, sorry. I always thought that it's based on subscribers. So that's why I said if there's 100 subscribers, there's going to be a special lecture, something that will be a picture prize. But it's not based on that. Okay, you can delete your subscribe. Okay. Yeah, of course. All right, now, mass matrix. That's what we're going to take a look at next. Okay, so what came from the previous mass? Let me show that to you again. So we got this component here. This is what we got. And now that one is called as a mass matrix. That will be multiplied by acceleration of generalized coordinates. And now what we're going to do next is we're going to look what are the details of the mass matrix. Now first, very important observation is this. That the mass matrix consists of 3 components. And this is already a big news for you, because I'm sure you heard the mass of the body. You know that the weight of the body, how much it weighs. I'm sure you heard that. That is related to translational motion. How much is the weight? What's the mass of the body? And I'm sure you have heard the mass moment of inertia. How much the inertia resists the rotational motion. I'm sure you heard that too. Those are the 2 components that you're familiar with in previous classes. But then we have a third component. Is there a problem? So it's comment. Camera is frozen.
Yeah.
Never mind. It's just that what is that? How much you're going to lose if you don't see my face? Nothing. I'm sure you're feeling better if you don't see my face. Smile face. Yeah. So let's just next time I'm not going to take a camera with me. All right. So yeah. So the third component. So I explained that there is a mass of the body, there is a mass moment of inertia that resists the rotational motion, mass of the body resists the translational motion. Heavier the mass, harder is that to push in translational direction. Higher the mass moment of inertia, higher is, the harder is that to rotate the body. That's how it is. Third component is something that is very unique. And it comes from the fact that the body reference coordinate system can be located anywhere in the body. If it is located in the center of the mass, then this third component that is here and here will be equal to 0. But if not, then it couples translational and rotational motion. Okay? So that's what we need to look at a little bit in details. But let's look like, okay, what are the first components? So the first component is the one that is located in the upper left corner of mass matrix. And that simply is 2 by 2 submatrix. Submatrix, which is a very important submatrix that is a diagonal submatrix. And the diagonal components are mass of the body. All right. So now if you look at the 3 by 3 mass matrix, this is located here and is obviously associated to generalized coordinates Rx and Ry. All right. So it means that if there is a heavy body, acceleration in a global X or global Y direction needs a lot of power, a lot of forces. So it's related to that. What about the one that is located here in the lower left corner? That is a mass moment of inertia. By the definition, this can be written as it is shown here. So we need to scan each one of the particles within the body by using the vector U-bar and then take the density into account. And this is a definition of mass moment of inertia. And it comes here in this component. And if you think about what's this generalized coordinates, it is associated to rotation. So it's clear. So the first two are related to translation, and then the theta component is associated to rotation. And now then the third one. The third one is the one that couples the translation and rotation. There is this mass matrix, the translation rotational matrix that is rotated 90 degrees in a positive direction, and then the vector U-bar. Now the vector U-bar, because it's just the one vector U-bar, if we are located in, if this is a body, we are comparing that component. This is where the body reference coordinate is located. And if the center of the mass is in a very same location, because of the nature of vector U-bar, this component will be equal to 0. But if I take my body reference coordinate system and put it in another location, then this component will be not equal to 0. Now that's what it is. Now the big deal is this, that this component here, this third component, is a function of body orientation. Never come to my office and say, okay, the inertia of the body will be function of the body orientation. This is a mathematical representation of mass matrix, and this is because depending where we're putting the body reference coordinate system, mathematical representation depends on that. That's what it is. Okay, makes sense. I know that you guys are confused, but let's practice a little bit. And let's practice this. So I have here rectangular planar body. The body frame of reference is located in the center of the, in the center of this rectangular body. And the dimensions are such that the h is a height of the body, L is a length of the body, and the thickness of the body is assumed to be W. Now, my task here is to define a mass matrix for this one planar body. Okay, mass matrix, what's going to be the dimension of the mass matrix? Let's get started from that. The mass is associated to generalized coordinates. Let's vote. So the chances is that this is a scalar component. Let's put it like one component, scalar component, 2 by 2, 3 by 3, 6 by 6, N by NB. Okay, now you need to vote. This is not the serious, but I need to see like how much you understand my talk. Who is voting scalar component? No one? Who is saying that the mass matrix will be 2 by 2? 2 by 2. Few guys, 3 by 3. You saying that? 6 by 6. N by NB. Okay, the correct answer is 3 by 3. Because, you know, it's always related to generalized coordinates. How many generalized coordinates we have here? 3. So you're my man. Okay, it's okay. So we have to have a matrix that eventually is having 3 by 3 or size of 3 by 3. Okay, so let's calculate the submatrices. So the first submatrix we can compare is related to mass. So we simply take the volume integral over the density of the body, and I have here identity matrix, which is 2 by 2 identity matrix. Then I take the thickness into account, so that's a W, and then I integrate from the limit, which are minus L by L divided by 2, because this corner along this axis is located in a place which is minus L, or is minus a small l divided by 2, until this point here, which is L divided by 2. And then I can take the y direction, which is minus h divided by 2, h divided by 2. I'm not going to touch the details here, so what I will get as a result is a volume multiplied by density. That's going to be equal to mass. That multiplied by 2 identity matrix. This is what I got as a final result. That's the first submatrix that I need here. Let's then compare the second component, the one that couples the translation and rotation. So this is an equation that I can use to make it happen. So I have here vector u bar, and now I write the vector u bar as a vector. And when I do this integration, you can see when this u bar integrated from minus L divided by 2 to L divided by 2, it's going to be 0. The same to this direction, so this disappears. So it's going to be vector of 2 components that are both equal to 0. What about my final component? That's going to be a mass moment of inertia. So it's going to be vector u bar power 2 x-axis, vector u bar power 2 y-axis. So I simply do the math. So this is very mechanical along these boundaries. When I do that, this is what I got as a result. So it's a mass divided by 12, then length power 2 plus h power 2. Fine. My final mass matrix look like this. Diagonal representation. Why it is diagonal? Because the body reference coordinate system is located in the center of the mass. Okay, makes sense. One more example. I know that it's already time to have a break, but I'm going to have another example. After that example, there's an in-class quiz, and then I will stop. Try to put the projector back on and look there if there's something else that I can do to make this a little more enjoyable. Nothing that I can do to make this lecture more enjoyable. It is what it is. No way. Okay. Now I have the same body. The difference between this example and the previous example is that the body reference coordinate system is located in one corner of the rectangular shaped body. Okay, what's going to be the size of the mass matrix? Scalar, 2 by 2, 3 by 3, 6 by 6, 3 by 3. Correct. Is this going to be diagonal, or is there going to be something that is off diagonal?
Diagonal.
Diagonal. So you're saying that this is a diagonal? No, it's not. It's not. Because the component that couples the translation and rotation will be not 0 in this case. Why? Because the body reference coordinate system is not located in the center of the mass. This is a question that I'm asking you in my in-class quiz. So, seriously. Today I will ask it 2 times. So you will have a first opportunity to check it out, and then I will reorganize the works, and I will ask that again, because I really would like to see one thing to happen, and 100% the high success rate. So that's why I'm asking things twice, not once, but twice. So if there is a question related to this, you already know the answer. Okay? Now here is not going to be the diagonal representation, because the body reference coordinate system is not located in the center of the mass. Clear? Okay, let's do the math. So what do you think? The first 2x2 code matrix will be exactly the same that in the previous case, of course, because the body mass is not the function where the body reference coordinate system is located. So if it weighs 10 kilos, it doesn't make any difference where you're going to put your body reference coordinate system. It's going to be 10 kilos. Correct. What about mass moment of inertia? Is that going to be the same that in the previous example? No, it will not. It will not. The camera is frozen, but if you're rotating the pen here in the middle, it's much easier than rotating that in one end. You can feel that. There's a difference. If you rotate it here in the middle, it doesn't need much power. I have a lot of power, so no problem. But still, here it needs more power. Why? Because the mass moment of inertia in this case is higher comparing to this case. Correct. All right, so we're going to have a different numerical value in this case. How is it going to be the numerical value? Okay, that's going to be next slide. But here's the one that that combines the translation and rotation. So I have here simply, the rotation matrix that is differentiated with respect to angle theta, with the U-bar that scans all over the body. And now the boundaries are here, from 0 to L, 0 to H, because the way the body reference coordinate system is located. And simply I do the math. I will do the computing. What is going to be my solution after that? It's going to be length multiplied by h multiplied by w, and then this is L divided by 2h divided by 2. That's how it's going to be. And then the matrix here, that is the one that is rotation matrix differentiated with respect to angle theta. And my final solution is a vector of two components. That is a function of angle theta. So it's a function of angle theta. So it really depends how is a body orientation. Okay? My final component is a mass moment of inertia. So it's a mechanical math. So I will take this vector u bar, these guys, these components, and then I will do this volume integrals. And what I will get is this one here. Remember, in the previous case, it was a mass divided by 12 multiplied by L power 2 plus H power 2. Now this one here is mass divided by 3. Okay, numerically, this one here is higher than this one. Makes sense? Because it is harder to rotate that body in one corner comparing when try to rotate that in the center of the mass. Makes sense? Okay, now to my in-class quiz, which is this one. Oh, this is how when I'm putting things together. So this is how finally the 3x3 rotation matrix look like. My in-class quiz is this. I have here rectangular planar body, and I'm saying that the body reference coordinate system is located in this particular location here. I'm asking which one of 4 choices is the mass matrix of this body. The first one is one that looks very complicated. Sometimes complicated may be the correct one, because more complicated the better it is. Correct. Well, I don't know about that. And then there is a diagonal representation. Then there's a 2x2 representation, a skew symmetric 2x2 representation. Okay, let's put the squiz on.
We didn't enter our names when entering this group.
You should. You should.
No, if you activate the question, then we can put in our names. So it is there.
Okay. All right. So now here's the hold on. So it's not dead on.
No, no.
Okay. Okay, now it's on. So, well, okay, I need to put this this system back because otherwise you can't really see what are the options. Okay, so these are the options. So you need to take a look at this slide from the YouTube, and then use Socrates to enter your answer. Once you're done with that, then you can. Then we're gonna have a break of 10 minutes. 10 minutes, and during the break, I will do my best to put the overhead projector on, and I will do my best to make the camera not the frozen all the time. Okay, that's not the good camera. Get this, yeah, it's not frozen anymore. Then let's see what's up with this guy. Okay, once you're done, then you can go and stretch your muscles a little bit. And I will close the recording, and when we're coming back, then we're going to look at the results.